welcome everybody. For those who have been on the previous meetups, this time it's me, no Sam anymore, unfortunately, but I hope you'll like it anyway. We're here for the speakers anyway, right? So it doesn't matter. So yeah, I'll start with that. Welcome to our speakers today. This time we have 3 speakers, although we have 2 talks. So warm welcome again to Hanna and Jörg for the first talk and for Rafał for the second talk. But before we go to the talks, yep, a little bit of housekeeping, not picking, housekeeping. So I went too fast. So first thing first, our code of conduct is available on softwarecircus.io/code of conduct. In shortcut, it just says, please be nice to each other. Don't do anything that could harm others. It's also open source, so if you want to use it for your meetups or your any other stuff, then feel free to do it. Yeah, the agenda for today, we still have 2 minutes. 2 minutes, so I need to speed up. So we still have 2 minutes for housekeeping. Then we're going for the first talk, Istio, Linkerd D2, or something else maybe, a comparison of service mesh implementations by Hanna and Jörg. To be honest, I'm pretty excited for that talk myself. I did a lot of service meshes in the past, so I'm really curious about that. Then we'll have 10 minutes for the Q&A. And then we go into the second talk at 7 p.m. Architectural caching patterns for Kubernetes by Rafał. And to be honest, I'm excited for that talk as well, because I just finished one of the projects for one of our clients where we implemented caching in Kubernetes. So I'm really curious to see how will it land in that talk somewhere. Then we'll have, of course, Q&A for Rafał, and afterwards we'll have 10, 15, 20 minutes just to chat, just to talk. So next thing, if any of you want to submit a talk, want to become a speaker for our next meetup, feel free to do so. We're always looking for speakers. You can submit it at bit.ly/talk@cs. I will post all the links soon in the chat, so don't worry if you can't copy it now. Another thing, you are free to join on our Software Circus Slack channel. So again, we'll have Q&A sessions after the talks as well. But of course, if you have some additional questions later on, or if you want to test yourself, Istio, Linkerd, and other service meshes, and yeah, want to compare your findings, you can always do that on our Slack channel. I will share the link, of course, as well to that as well. This session is recorded like any other Software Circus, and it will be available on YouTube afterwards. So as I said, some people may go out today for the beautiful weather, but the talks will be available. And this Software Circus in general was built by us. I'm working for Container Solutions as well. It's powered by Container Solutions. So just a few words about us. We are a cloud native consultancy company. We are helping with anything cloud native related. We are hiring as well, so also feel free to check out our website if you're interested. And you can sign up for our newsletter. We are now running series of talks, events under one umbrella. What the fuck is cloud native? So we try to explain different topics around cloud native in more, let's say, easy language. So yeah, that's it. 1 minute past. Sorry about that. So yeah, let's go to our first talk. Hanna, Jörg, stage is yours.
All right, thank you. I will just try to do the screen sharing, and then Hanna will say a few words in the beginning. Yeah, let's do it this way.
Yeah, so welcome everyone. Thank you for joining. This talk will be about the service mesh options that are on the market, and we will do a comparison of the things that we think are most important in this space, because I don't know if you are aware, but I think we have 7 or 8 service mesh implementations right now. And you know, the space has been growing a lot, and we will try to, give you an overview and decision-making support. So a few words about us and InnoQ, the company we are working for. Yeah, my name is Hanna. I'm a software developer, mainly in the space of DevOps, cloud native infrastructure, Kubernetes, and I have been working on the topic of service mesh a lot for the last 2 years. And
aus Deutschland.
Yeah, we're in Berlin, Jörg and me, actually. Yeah, so Jörg.
Yes. So my name is Jörg Müller. I'm also principal consultant at InnoQ, concentrating on software architecture stuff, DevOps development, and the focus in the recent years has also been the infrastructure area, everything that you need to run software on. I just heard that one of our hosts has a lot of experience with service meshes. Well, I will still start with a little bit or some few words about what is a service mesh if you haven't done that in the recent time or have not seen service meshes yet, so that you know what we are talking about. And then we will go about what options exist and what how do they differ from each other. Okay, so service meshes. And what problems do they try to solve? So where do service meshes come from? We have in the last, let's say, it's nearly 10 years now, tried to build distributed applications and called them microservices. They are beautiful and nice because they are small and everybody can think about that and can think about a certain service. But if you come into the situation that you have more of them and you have a larger project, you will find that they are simply distributed systems and they have problems. And they have problems you have to solve. Problems like routing and discovery. You have to find your service from one service to another service. You have problems like timeouts if there is one service not available. So you have to set up timeouts. You have to care about them. You have to care about retries if there is a timeout and make sure that you are not retrying too often to crash your whole system. So you have probably to care about circuit breakers where you have a possibility to say, okay, one service not available, so we don't call it for a certain time and try it after a while. You probably might want to encrypt your traffic between your services. It's at least very often a quite good idea. And you might want to check whether the service you are calling or the service that calls you is allowed to call you. And so you need to take care about who's calling me and is he or it or whatever allowed to do this. And last but not least, you want to have some metrics and some logs, and you want to collect them. So quite a lot of problems you need to solve. And there are options to solve those problems. And one of the first ways we did was we used libraries. So we created libraries. Netflix did a lot of that stuff, but also other companies that helped us to do all those tasks again and again. And that's very often a very good solution, but one of the promises of microservices was we want to have technology independence. We don't want to care about just a specific technology because otherwise we could just use Java web servers or something like that. So libraries are not a good solution if you want to go into a more heterogeneous way of your services. So that was an option, but maybe not in all situations. Then there was, of course, Kubernetes. Kubernetes helps a lot with spreading your workload on several servers, with network issues, with questions how one service finds another. So a lot of things are solved there, but still not all of them. And there are still some things in the routing and stuff like that that are not the complete thing you need or you want to have. There comes the idea of service meshes. So a service mesh puts a proxy aside of every of every microservice, or just let's call them services, not necessarily microservices. Every service that runs has a proxy that catches all network traffic. Well, to be honest, it's not all service meshes that use that principle, but most of them, the majority. And these proxies can do certain things with your traffic. So you can measure what traffic happens. You can lead your traffic somewhere else. You can stop it. You can delay it. You can do a lot of funny stuff. But if you have a lot of services in place, then you want to control that on a central place. So this idea was actually already there before service meshes. There were things like Smart Stack, how it was called in, I think, 2012, 2013, that used the same idea of putting a proxy just beside any other service or on any server. But doing this combined with a control plane that then can remotely control how the proxies behave and what rules they apply, that's the idea that was the core of a service mesh. So if we look at let's call it architecture, we have some funny layers here. You can say that you have something like the application layer where your service is running. You got the data plane where your proxy is running. So service meshes are using the same terminology that we know from network equipment and stuff like that. So they say, okay, we have the data plane that carries or that takes care of the real traffic, and the control plane that controls how everything is working together. And then you got certain infrastructure that you're communicating with. It's the Kubernetes API in many cases that allows you to find out what services do exist, what services do we need to take care of, and other infrastructure services like monitoring systems and stuff like that that you're interacting with. So now we know, okay, what problems do they try to solve, and the basic ideas of service meshes and how they solve that. And there has been a lot of hype about that because there are a lot of people that run into those problems and try to solve them and think, okay, service meshes are a great solution for doing that. But in all of those cases, you should ask yourself the question, do I need a service mesh at all? So before we go into what implementations are available and stuff like that, we should take a short look on some questions whether we need a service mesh or not. And it might surprise you in a situation like that or in a talk like that to hear that very often the answer is no. There are a lot of reasons why service meshes are probably not the solution or the thing that you should go for by now. I will try to give you some rules of thumb, some ideas, some hints that could show you, okay, a service mesh might be a good solution, or maybe there's other stuff you should focus first. Well, one of them is how many services are you actually using? There's no hard number that I can tell you that says, okay, if you're using more than 5 services, then you definitely need a service mesh. We were thinking a little bit hard about that, and we said, okay, at least a minimum of 10 services should be there, because otherwise you probably don't really benefit from all the automation, and the complexity of the service mesh will then be much bigger what you handle there than the benefit you have. So if you, but that might not be a hard reason to say, no, you don't need that. So if it's 9, you still might need or might benefit from a service mesh. If there are, for instance, certain features, I will come to that later, that you need to implement where a service mesh is where a service mesh can provide those features very easily, and other ways would just be more complicated. The next thing is ask yourself about what diversity of technology do I use in my services? Because I said already that libraries are an option. And if you're still a company that uses Java all over the place, and you're not going to change that, or you don't want to change that, then it still might be a good idea to just use libraries. So there wouldn't be a hard indicator to say, oh no, you should definitely use service meshes for that. Libraries might be good too. and might solve your problems. So you might take a look at them. The next question is, how do your services communicate to each other? Because service meshes are especially made for a situation where a lot of your services are communicating in a synchronous way. So one service calls another one and waits before he gets the answer to his caller and stuff like that. This is not necessarily, or in a lot of situations, this is not a very good idea to do at all. And a lot of architectures that we know and that we use at customers are asynchronous. And if you have an asynchronous message-based or pull-based architecture, then the benefits of a service mesh are much smaller than if you have a synchronous one. You just have to know that. So that might help you in a decision. The next one is a very big one. It's the question, are you already using Kubernetes? Because if you don't, then you will see that later. Most of the service meshes on the market will just need Kubernetes to run. And the two big, Istio and Linkerd too, definitely do. And most of the others too. So first of all, if you're not using Kubernetes, you're restricting your options for service meshes very much. But that's not the only reason I say that. Because if you are not using Kubernetes, it might be that you are not, you just don't have the problems or the problem area that you need to do, or that you need to also have service meshes or to solve problems that service meshes solve. That does not mean that that systems that don't use Kubernetes are just simple systems. They are very often very complicated, but still it could be an indicator if it's just a few servers that you're using, that service meshes are just not necessary in the environment you are. And another reason to look at whether service meshes are necessary or not is actually how dynamically do your services change. Service meshes are very strong in steering environments where services change very often, be it because of new versions or be it because you have a dynamic scaling. And not all of us need that. And there are, I don't know about the Netherlands, to be honest. I do this talk in Germany too. And we have a lot of customers in Germany, especially in these small mid-sized companies who just don't do a very quick change of their software. Where I am not saying that this is a good way to do software, it's not. But if you're not even doing real or some kind of continuous delivery and stuff like that, then probably service meshes are not the first thing you should look at. You might have other reasons to change your software. You might need to look at other things before doing that. So, but last but not least, still there are certain features. If you need them, then service mesh might help you very much. The first thing that always comes into mind is encryption, especially encryption based on MTLS. MTLS is mutual TLS, so like the usage of encryption on your web page in normal TLS, where you know that the server is really the server you're talking about, you want to talk to. Mutual TLS means that also the server tries to find out whether your client is also the one that is allowed to talk to him. And you have an encryption in both ways. That's quite a complicated thing to set up if you want to do that manually or without service meshes or something like that, because you need to care about certificate issuing, you need to care about rotation of certificates and stuff like that, and enforcing of all those encryption stuff, which is not easy if you do that by hand. Service meshes can probably just implement that in a very short time, because most or many of them just come with that feature included and can just apply it. The same is true for tracing specific routing requirements, like you want to do Canary releases and stuff like that, where a service mesh can just help you so much that it's completely all the other reasons I gave you for maybe not looking at it are just overruled. Okay, so we know that, so we think or we assume that we need a service mesh. Then you have the choice, and it's it's a pretty large choice if you look at the implementations that are in the market. And we definitely can't look into all the details of all service meshes in a 40-minute talk, but we try to give you an overview what meshes exist and what is their difference. So let's just go through all the meshes here. First thing you will probably already know if you heard about service meshes is Istio. Istio is a service mesh that has been created by Google and is now supported by IBM and several other companies, which is a very powerful one and at least was a very complicated one too. They are working very hard at the moment to simplify the installation process, to simplify the components in the service mesh and so on and so on. But it's for a long time, it was kind of synonymous for service meshes. It's not any longer. So the other versions or the other implementations are very capable too already. One of them is Linkerd. Well, if I say Linkerd, I mean Linkerd 2. There is an old version of Linkerd that was JVM based, but which is not really supported anymore. You will, if you install Linkerd and if you talk about Linkerd these days, you are talking about Linkerd 2, which is developed by Byrant, and they are using a Rust-based proxy. So proxies and which proxies are used is also one of the features that can distinguish the service meshes. We will see that. And a Go-based control plane, which is pretty compact and easy to install, to be honest. Then there's a lot of meshes that are based on other products that have been there before, which absolutely makes sense because they solve a certain area of problems, and there are products that have been solving problems in those areas before, and using the idea of service meshes to extend those makes absolute sense. One of them is, of course, Consul. Consul is one of, or is a very, very popular service discovery solution that has been there before Kubernetes. A lot of companies are still using it. They extended their functionality for service mesh functionality. So if you are using Consul today, that might be a useful thing. Then, of course, there's a solution from AWS, which is very uses the same proxy like Istio, is very nearly like Istio, but also includes a lot of other AWS services. So if you're running in an AWS environment, it might be something to look at this. There is Traffic, which is a reverse proxy that was is very popular in the in everything around containers, because it has a very good API, has a very good interaction with the Docker API with Kubernetes and stuff like that. And of course, they also have they have a proxy already, so they just need to add a control plane, and this is what they did and called it Traffic Mesh. There's Kuma, which is based by the same company that uses or creates the service mesh Kong. Sorry, not service mesh, the API gateway. And of course, API gateways and service meshes solve the same region or area of problems. So it makes total sense to use that. Some newer players, well, new for Nginx, but I come to that. Some newer entries here is Open Service Mesh. Open Service Mesh is based or is created by Microsoft, and it's based on the Service Mesh interface specification, which I will come to in a minute, and understands itself as some kind of a reference implementation. But because it's Microsoft, it might also be something for maybe Azure in the future that might become important. And Nginx actually has tried to create service meshes several times. There was an approach a few 2 years, I think, ago, which was really based on the proxy and not on Kubernetes, which somehow died over the time. And they now created a new version that is based on Kubernetes. And is actually pretty powerful compared to the other ones. Okay, so if you want to have a little bit more of a detailed overview of that, we had the funny idea to use the domain servicemesh.es to create a website for comparing several options or several possibilities. You can take a look at this site and you will have a lot of detailed comparisons. We will not go into this detail in that talk, but you will find everything about what kind of features are supported or not supported. And if you find any errors because you're developing a service mesh on your own, then please let us know. Just it's just a pull request away to change that. And just a few of those service mesh implementers like Consul are regularly doing this. So we are pretty certain that this information is accurate. Okay, so choosing an implementation. How do you do this? And what do you have to do? What questions do you have to ask yourself? Well, the first thing you have to ask yourself is, in what environment do I want to use the service mesh? And there are a number of questions that you can look at. It's what infrastructure do you run your software usually on? What is in place? What are your preferred cloud providers? Maybe that matters. What knowledge is already available in your company? Are there products you're already using? And last but not least, how flexible do you want to be? Do you think about exchanging your service mesh or changing it during the lifetime of your application or not? Probably, I mean, like ORMs, I think this will not happen very often, but still it's an idea that you might have. Okay, so first of all, where are you running? I already mentioned Kubernetes. So if you look at the service meshes, and I said that before, then most of them are Kubernetes only. And most of them is especially true for the most popular ones like Istio or Linkerd, which are just which are using features of Kubernetes to run, and they just can't run in any other environment. There are some solutions. So if you are not using Kubernetes, that you can use outside of Kubernetes, which is Consul, of course. If you're using a Consul network, especially, you can use Kuma outside of Kubernetes, and you can use the AWS App Mesh with Kubernetes, but also without, but then only in AWS services. This is one of the points. If you talk about what infrastructure am I using, what cloud provider am I using, then of course you can have a look at what cloud provider is in place, what is your preferred one. Then, well, if you're using Kubernetes, the impact is, to be honest, not very big. So there are not hard rules to do that, but there might be some hints. Like, for instance, if you're using AWS, and especially you want to use a lot of services like Fargate or ECS that are not based on Kubernetes, and you want to integrate them into a mesh, then this is definitely something you should have a look at. If you are using Google Cloud, for instance, there is a very easy integration of Istio into GKE. So the container engine, you can at least use Istio by just setting a check mark and running your cluster. Well, it's well supported. In most cases, it's probably not the way that you just set a check mark. You will want to do some other stuff too, but it could be good. And if you're doing Microsoft Azure, then you might have a look in the future to Open Service Mesh. I mean, Azure supports Istio, supports Linkerd. There are pages that describe how to set that stuff up. So you're definitely not locked into OSM, but it might be interesting in the future. I don't think I would currently use that one in any production environment. And then the already mentioned service mesh interface. So the several companies that offered service meshes realized that it might not be a good idea to have every service mesh do its own configurations, and it might be possible to create a standard for for definitions of specific stuff that a service mesh needs, and then let that be independent, or have independent implementations of this standard. What they do is they created, or what they did is they created a number of custom resource definitions in Kubernetes that can be used to describe how service mesh can behave in some way. There are things like traffic access control, so what service can be accessed by what service. Traffic metrics, so to define what metrics do you want to read from a service. Things like traffic specs, so you can go down and define what kind of traffic is really happening there, so you might have better metrics on that. And the one that's very popular in usage is the traffic split, so you can define how traffic is split between services. So this is the thing. You can find that on GitHub. There are several versions. All of them are alpha. They have differences. Some of them are pretty big. And it also differs which service mesh implements which version of this SMI spec and so on. So I'm happy that they are trying to do this, but you can't say that just because you're using SMI, you can just switch between service meshes. That's definitely not true. And especially not because not all of them are supporting the spec completely. Well, to be honest, only service mesh, or open service mesh, does really support the spec completely by its own. There is an Istio third-party version that supports SMI, so that Istio can implement SMI CRDs. Most of the service meshes support only a part of it. So Linkerd supports mostly traffic splits and will do some other stuff like access control in the future. And some of them just ignore the SMI specification, like AWS or Kuma. Okay, so with that, I would like to hand over to Hanna to talk about what features are needed, for instance.
Yeah, so the question you will ask yourself when you decide about a service mesh is, what features do I need, or what features does the service mesh provide? And what we recommend as questions is, first of all, what are current challenges in your project? So because some features you might want, but maybe some challenges are more pressuring in your project, and you should focus on those. And also, I would think about what are things that I would like to have if I can have them, and what do I really, really need? So because if you go with the decision like, okay, I want to get everything, then your choice might not be the best one for your project. And also, how many things do you need to configure? Because some service meshes introduce a standard, and they don't let you configure everything, while others let you configure pretty much everything, which of course lets you, make you end up with a lot of code you have to maintain for the configuration. And finally, how much effort do you want to spend with the service mesh configuration and the feature configuration? But let's go through all of the, let's say, categories of features. Let's start with routing. So the main feature of routing is probably, as you might have heard, Canary releasing and A/B testing. So you can manage Canary releases and A/B testing with the service mesh. And the easiest thing to do is to split the traffic for service B to 90%, let's say the stable version, and give 10% to a Canary version that you want to test. And afterwards you can see if the new version, the Canary version, performs as well. But you can do even more, because there's also the option that you can have a path-based split. So whoever knows maybe a secret path in your domain can access the Canary version. Or I think that's most useful for people. is to decide about which version to use based on the headers. Because maybe you have location-based headers or some groups of customers that you want to give the new version to. So we have those different categories of routing capabilities, and also the service meshes, provide different support for those. So you should really think about, am I all right with just percentile-based splitting, or do I need more advanced header or path-based splitting? The next topic is resilience, which is a large topic in a service mesh. And what you can do is, as Jörg already said, is you can decide that you want to end a call within or after several seconds or hours or whatever you wish. And you can do this automatically, so you don't have to put that code in your microservice application, but you can just roll out the configuration for the service mesh. And you can also decide to make a second try, or a third or a fourth. Many service meshes let you define those rules. And also there's circuit breaking features in some service meshes. And the differences are very, very big. And I recommend you to take a look at servicemesh.es to see, which feature is implemented in which service mesh. And also because some meshes might let you configure retries, but they don't let you configure retry per endpoint. So you might have to define one policy for your whole service, which is sometimes not what you want, because there might be HTTP post requests that you don't want to be retried. So there are really some tiny differences that can be important for you. Then there's chaos engineering, which is pretty much a controlled, breaking your application in a controlled way. And what you can do is fault injection. So you can let the service behave as if it returns failing responses, or you can delay responses. So you can do experiments, and you can check assumptions that you have around your application, your stability. Those things are supported in Istio, for example, but also in Kuma, and some of those things are also possible with Linkerd too. But there's also some details that you should take a look at, because the complexity of those configurations can differ pretty much. Then there's security, which is, I think, the most pressuring thing for many projects, because as Jörg said, if you do this, yourself, then first of all, it's not very secure most of the time, and second, it's a lot of work. So what you can do with the service mesh is you can automatically have MTLS between all of the services. So because certificates are automatically provided by the service mesh data plane on a control plane. So the services can communicate in a secure way. And another feature that I would encourage you to check in the service mesh you're deciding for is MTLS enforcement, because some meshes give you the possibility to reject calls that are not performed with MTLS, while others just allow MTLS when it's possible, and if not, they will just accept all other requests as well. So luckily, most service meshes support MTLS. I mean, this is what service meshes are really good at, right? So to provide features on the network layer, you need for all your services. And the differences are if MTLS is also possible for TCP connections, and also this MTLS enforcement that I just talked about. And finally, there's observability features. So first of all, the quality of the dashboard that you will have and most of the service meshes is really different. I will show you the one for Linkerd. So this is the dashboard you will get with Linkerd. So you will see a graph-based or two graph-based views on of your services, with colors indicating the health, with statistics like how fast your services respond, a lot of details. There's much more to it, but this is just like a quick demonstration. Whereas this is Kiali, this is the dashboard of Istio. This is much more graphical. You know, you can have all this data that we just saw on the tables in a graph, and you can also change the graph to whatever you want. There's a lot of options you have. You can have requests per second on the edges, or the request load, or pretty much whatever you want. So this is also depending on your taste and your needs. Yeah, but I must say that I find Kiali very, very useful for a first view. But Linkerd has a better API sometimes to get all this data. So I would really take a look and decide based on some experience. So, but with observability, there's not only the dashboard, there's also the question of if Prometheus, Grafana, and Jaeger, which are, the basic monitoring tools that are on the market and also used by service meshes, the question is whether they are pre-configured in the service mesh and to what extent. And also if tracing is even supported, because most of the service meshes give you also tracing features and integrate with Jaeger. And also there's access logs, which I'm not sure if this is really useful for most projects. But if you wanted, you have also some options here. And also there's slightly different features like Linkerd tab. You can check which can do similar things, but has a slightly different opinion about how you need access logs. So the final question is, apart from all the data you can have about service mesh implementations, is like the subjective fit that you need. So the first thing that also might be, a bit more on the data side is production readiness. And there's three things three implementations I would categorize as leaders in the area. And that's Istio, Linkerd, and Consul. And these are also, most of them are led by companies who have a lot of experience in this space. And then there are some that are, I have categorized them as followers. So they have also a lot of experience, but they are not on the market as long. So they are maybe not that battle proven. And then there's Open Service Mesh and Nginx Service Mesh, which are just pretty new, and they have not reached the version 1.0. So maybe these are some that we will have to wait a bit to decide finally. The next thing you want to look at is the complexity of configuration, because as we said, there are very different teams, and some can handle a lot of complexity while others cannot. And I think personally, I think this is the main decision, one of the main decisions around service mesh, because you need to take care of this thing. You install it once, and then once in a while you have to update it, you have to reconfigure it. And I would really take a look at the configuration interfaces, because something easy like traffic split, where you split the traffic between 90 and 10%, some meshes allow you to configure it with 10 lines where others need 30. So I would really, take a look at the code and do some experiments. And also, as we speak of complexity, always keep in mind that if you introduce a service mesh, you have more things to check when something goes wrong. So you don't just take a look at the ingresses and the microservices. You also have to check the proxies, both proxy configurations, and the control plane of the service mesh, and also, just like before, Kubernetes and the cloud. So you have many points where things could go wrong. So you need some experience, and so just keep that in mind, and also try to find out which service mesh might be best for you in the effort of debugging. And of course, service mesh has a performance impact. This is the question we get pretty often. It's about 3 milliseconds for each request between microservices that it adds up. Maybe more importantly, it adds to the bill. You know, you need additional CPU memory resources in your cloud. But these things differ pretty much on the service mesh implementation, but also on your architecture, you know, like how many services do you actually have, and how much do they communicate, and what amount of traffic do you have. And there are some official numbers, but I would really tell you to do your own benchmark, you know, deploy your application with or without service mesh, and measure the numbers that you get for latency, and also for CPU and memory. Right. So finally, some final words. So if you are approaching the topic of service mesh in your team and your project, I would recommend you to check the technical environment, like Jörg said, the Kubernetes support, the cloud infrastructure tooling around it, and think about what features you really need and what are the musts and nice to haves. And then take a look at our table maybe. And then think about subjective things like production readiness, developer experience, configuration, and also do some tests around performance. But as Jörg said at the beginning, the first question would be if a service mesh is actually the solution of your problem, or maybe your problem is somewhere in the architecture or somewhere else. This is where I would look first, because it's another complex piece of technology that you will introduce in your system. And if the problem is not there, then it's not worth it. So if you are curious about the topic of service mesh, then here are some links. We will also share the slides on Meetup and on Twitter. On the right-hand side, on the corner, you can see our handles. We will share them there, but also on Meetup. There's also some tutorials that colleagues and me did, and also a small book that you can download for free, where we explain things around Istio and service mesh in general. Yeah, and so thank you for listening, and we are here for questions now.
Thank you very much to both of you. Indeed, we have still a few minutes for the questions, so feel free to just unmute yourself and ask a question, or ask it on the chat and I will read it.
Hi, everybody.
Hi.
Thank you. Nice presentation. Very integrated. Everything you've covered, everything. I appreciate that. One question that I have is that if we can specifically, if you have experience regarding competitive comparison between the Linkerd and Istio service mesh. I have a lot of experience regarding Istio, but I want to know that I want you to share any experience regarding the Linkerd, and because I'm going to design a service mesh solution for one of our customers, and so Istio, as you mentioned, is complex. The learning curve is it does have a learning curve and something like that. And I had a small POC with Linkerd, and it seems that Linkerd learning curve is smaller than Istio learning curve. So I want you to share any experience regarding the Linkerd versus service mesh. Istio versus Istio, sorry.
Yeah, I can do that. Well, our experience is pretty similar to what you just said. So Linkerd is definitely the easier service mesh to just install and learn. So when we use it at customers that don't need specific features of Istio, we usually prefer Linkerd because it's just faster to install. It's pretty stable. It's easy to see how it works. Very well documented. But you need to be aware that there are quite a few things that Istio can do that Linkerd can't. So traffic splits, for instance, it can be really annoying. So you can only use traffic splits on percentage base in Linkerd, which might be a problem if you're doing Canary releases and stuff like that, because there you probably need, in reality, you probably need cookie matching or something like that to do those releases. You have some monitoring features that are not completely working in, or that are more difficult. Where I must say that Linkerd just released version 2.10, which, for instance, makes from my point of view, the Jaeger integration much easier, or it's at least there from the beginning. It was, I think it was a beta somewhere before. It's now pretty good to use, but still tracing was better. The Canary dashboard actually delivers more information on one hand, but on the other hand, as Hanna said, you can use a lot of, or you can get a lot of those data that you usually get on the dashboard also on the command line in Linkerd, and then in a JSON format, so you can automatically processes and stuff like that. That's something we really like a lot. Getting stats and stuff like that. Tab feature of Linkerd is very, very nice if you want to do detailed debugging, because you really get any call in detail, from which pod to which pod, what was the latency, what was an error and stuff like that. So if you have problems between your services, then Tab is absolutely brilliant to do debugging. You need to take care a little bit if you are in a production environment, of course, because the amount of data that you can generate with Tab is pretty big. So those are the features. So there are things that Istio definitely can do better. So Istio is the more feature-rich framework or service mesh. Linkerd is the more compact, more easy to install, more easy to get to grasp service mesh. So I would usually go the Linkerd route if I don't need features of Istio. That's my conclusion.
Yeah, I agree.
Sorry, what was your last sentence?
I would, in a project, always go Linkerd if I don't know of features in Istio that I definitely need.
For example, like cookie-based traffic splits.
Okay,
Yeah.
thank you.
All the stuff I got. Yeah.
But also keep in mind that all the projects are progressing, and features might be on the roadmap and could be added. So maybe you can check the issues on GitHub and see when features will be added. So maybe this will also impact your decision.
That said, Istio reduced its complexity immensely in the recent months. So an Istio installation of today is much, much easier than it was 12 months ago.
Great. Any more questions? I have one in the meantime then. So
Sure.
Sometimes I'm getting the question from the clients that the only thing they care about is to encrypt the traffic between microservices, right? So then they ask me, oh, but Istio can do it. Istio can do MTLS. Would you, what you're thinking about it? If the only thing you want is to encrypt the traffic, would you still go with service mesh?
That's what I said before. But we have done in our company projects implementing MTLS before without service meshes, and they are usually a nightmare. And with service meshes, this gets really, really easy. By the way, there's also, I've heard, there's also an area of features where Istio is much stronger than Linkerd today. For instance, you can't do any authorization between services in Linkerd. So if you want, or if you need authorization between services, you need to go the Istio route or some other mesh that supports it. But yeah, so MTLS encryption alone can be a reason just to install it. And if encryption without enforcing or authorization is enough, then just install a Linkerd. That might solve the problem in an hour or less.
Yeah.
But there might be some other alternatives in the future, like Cilium, for example, which solves the security problems on the Linux kernel. I will add a link now. These things are pretty new, but maybe in the future we won't need containers running for MTLS. We might be able to do this on a different layer. But right now I think it's under development, and I'm not sure if this is production ready.
Sorry, what was the name of the product?
Cilium. So this is, I also added the link in the chat. This is eBPF based. So it's a different approach than service mesh. So Cilium is not a service mesh, but it's a different solution where you can solve encryption with.
Maybe we can say that in general, the approach using the Berkeley package filter, so the eBPF stuff, is a very interesting one to watch. Also, observability can be done very nice on this level without adding sidecar containers. Some people from Kinfolk, you might probably know them, have some very good talks about that. If you haven't had them here, then I can recommend them. How to use eBPF for monitoring traffic in between. Very, very much like you would do it in a service mesh, but you just don't need the sidecar container.
We have a question on the chat. What would be the advantage of using that authorization that you mentioned in Istio versus, for instance, network policies?
Yeah, so Jörg, you want?
Okay, whoever wants. Okay, then I will do. So network policies don't necessarily go on such a deep level like you would do with a service mesh. So in a service mesh, you have, for instance, authorization based really on encryption. So on checking the certificates. I wouldn't think that this is on the level of the network policy. I mean, there you use service accounts and stuff like that. So maybe that's equivalent. You can go down to the level of pass. So you can do authorization on pass level, which is quite useful, which I think network policies is only level 4 stack, so TCP stack. But I'm not completely sure, to be honest, at the moment, whether you can do network policies on HTTP level, but I don't think so. So this would be another reason for using a service mesh on this. This is a general thing. Service meshes are very strong if you are going higher in the network stack. So if you're going on application level on layer 7 and want to do stuff based on HTTP calls or gRPC calls or stuff like that, then they are much stronger. If you only want to do TCP authentication and stuff like that, then you probably are very, very well off using Kubernetes standard things.
Yeah, I agree, because I think the question is really good. I mean, comparing service mesh authorization with network policies, because some products will make you reinvent the wheel, you know, because there are standard ways of doing authorization in Kubernetes, and I would always prefer using those. And only if you want to do path-based decisions in authorization, I would use the service mesh authorization.
Okay, thank you again very, very much for the talk. We are a few minutes after, so we'll go to our next speaker, but I believe Jörg and Hanna will monitor the chat. So if you have any more questions, feel free to ask them on the chat.
I have another question. If any experience on, I know that there is a Meshery. Are you familiar with Meshery? Meshery.io.
Yes, as far as I know, it's more like tooling based, tooling on top of service mesh, and also performance tools and also comparison. I'm not aware that they have a service mesh of their own. I think they are, you know, testing service meshes, let's say.
It's more like helping you installing service meshes in your environment and stuff like that. That's at least where I know them from. So they make it easy to install Linkerd or Istio or something like that, and make it easier to switch between them. But to be honest, I haven't worked with Meshery so far. I haven't seen the need yet.
Yeah, okay, thank you, thank you.
Okay. So our next speaker, Rafał Leszko, will talk about architectural caching patterns for Kubernetes. So let's do it. Rafał, the stage is yours.
Hello, everyone. I'm super happy to be here, and welcome to my talk called Architectural Caching Patterns for Kubernetes. Let me screen share, and we'll start right away. So you should see my slides. Firstly, I will tell you about like what different caching topologies you can use in Kubernetes, because Kubernetes brings some new things to the caching solutions, and how they affect your architecture of your microservice system. First, a few words about myself. So I'm a team lead of the cloud native team at Hazelcast. Before, I worked at Google and CERN. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking and trainings, but on a daily basis, I'm a software engineer. A few words about Hazelcast. So Hazelcast is a distributed company, and it's distributed in two meanings. At first, it's like distributed because we produce distributed software. Our products are Hazelcast IMDG, which stands for in-memory data grid, which is used for caching and for anything that for speeding up your system. Hazelcast Jet is a library for stream processing. They are both open source, by the way. And Hazelcast Cloud is Hazelcast put as a service. But we are also a distributed company. There's also a second meaning of this, because we all work remotely, and it was always this way. So from the beginning, the company was founded as a remote company. So I work from Poland. I work from Krakow, but I'm the only one actually from Krakow, and people are all over the world. Our agenda for today is pretty simple. So there will be a very short introduction about caching in general, caching in the microservice world. And then we will walk through all possible caching patterns that you can use in your system. While I'll be talking, I would like you to focus on two things. So the first thing is which of this topology, which of this pattern you use in your system, because you must use one of them. You most probably use caching, and this list is actually complete. So you must use one of this topology. And the second question that I would like you to ask is, would it make sense for my system to migrate to any other solution? Would it be beneficial for the overall architecture? And with this questions, I leave you to listen to this talk. So microservices. That is a classic microservice system. So we have a bunch of services, they have versions, they are written in different programming languages, they use each other. That's how we architect system nowadays. And now the question for this talk is, where is the right place to put your cache? Where should be the caching layer here? So should it be like inside of each service? Or maybe we should put cache as a separate unit in on our architectural diagram. Or maybe we should put cache in front of each service. And that's what this talk will be about. So the first caching topology is embedded cache. Embedded cache is the simplest thing you can imagine. So how it looks like. So that is the flow diagram. So request goes to our system. In Kubernetes, it goes to Kubernetes service. It's load balanced to one of the Kubernetes pods. And then inside the Kubernetes pod, an application receives the request. An application uses a caching library to check, okay, have I already executed such request? If yes, return the cached value. If no, do some business logic, put the value into the cache and return the response. So it's super simple. It's that simple that you can even implement it on your own. You don't even need a caching library. So if you like Java, that is how it could look like. So we can have like a collection, concurrent hash map, and then check, okay, have I already executed such request? Does my cache contains this request? If yes, return the cached value. If no, execute process, put the value into the cache and return the response. If you like, I mean, you can implement this in any programming language you want because you have collections everywhere. In Java, that's how it could look like. But first thing I want to mention is like you better not implement cache on your own. Because like simple collection is not good as a caching. It's not good because it misses a lot of features like eviction policy, like max size limit, like statistics, like expiration time, notification mechanism. So simple collection usually is not good enough as a cache. So what is good as a caching solution? So for Java, there is a lot of libraries, like the small one, but very good one is Guava, where you can define all these features up front. Another solution is EHCache. For basically any programming language, you will find a library which provides all this caching functionality. Now, we can move this caching layer actually one way up in terms of the abstraction and put the caching, not use the library directly, but put it in the application layer. So in Java, still most applications are written in Spring. So that is how it would look like in Spring. It's enough that we annotate a method cacheable, give it a cache name. And now every call to this method will first check if the given ISBN is in the cache called books. If yes, return what's there. Only if the value is not found in the cache called books, we execute find book and slow source method. But be careful because for some reason, Spring by default uses concurrent hash map. So you're better off defining your cache manager and changing this to some caching solution. So far, so good. So we have like a first caching topology. This diagram is good, but it has one problem. So this topology has one big problem. Imagine that there is a request coming to our system and it's load balanced to the application on the top. We don't have the value in the cache, so we do some long-lasting business logic, put the value into the cache, return the response, all good. Now, again, the same request goes to our system, but this time it can be load balanced to the application at the bottom, because like Kubernetes service, it uses like round-robin strategy, so it may go to any application. And now what happens? We need to again do our business logic, because these caches are completely separate. So they don't know about each other. So one of the improvement to the embedded cache would be to use embedded distributed cache. Embedded distributed, it's still the same pattern, is still the same topology if you look at the architecture, but this time we will just use a different library for caching. So I will show you how to do it with since I work for Hazelcast, I will show you how it looks like in case of Hazelcast. So again, request goes to our system, it's forwarded to one of the application. Application has library for caching, but this time, every cache from every application, they all form one consistent caching cluster. So no matter which cache we use, we have the same data. So it is very convenient, very consistent, like with this microservices. You create a lot of replicas of your microservice, but you still cache them all together. If we stick to the Spring example, how it could look like. So all we need to change is actually to define a different cache manager. So this time we define, okay, use Hazelcast as a cache manager. All the rest of your application stays the same. Now, you may think like, okay, we run multiple replicas of our application. So we have, but how it's possible that the caches, from each application replica, they form one consistent caching cluster? And we thought how to solve it, because, you know, it's need to be dynamic, especially in the Kubernetes world, when you don't even know what will be your pod IP address before you start it. And we've come up with the idea of something what we call discovery plugins. So Hazelcast actually automatically discovers, okay, I am running in Kubernetes, so I should use Kubernetes plugin to discover other Hazelcast nodes so that we join together. And then it uses Kubernetes API or Kubernetes service, you actually can choose it, to discover other members and form one cluster. If you use other not Kubernetes but other platforms, we also have plugins for them. If there is a platform we don't have plugin for, you can always piggyback on Euroka or Zookeeper. If you're interested in details how to set it up, we publish a lot of blog post documentation, so you can look for this. So we ended up with this diagram, embedded distributed cache. So let's do a short summary and describe pros and cons of embedded caching. So from the good side, so what is good about embedded caching? First thing that is good is this is very simple. We just used a library. There's nothing more. So you don't need like an ops team to manage your cache cluster, because it goes together with application. You also have very low latency data access, because you cannot do anything better than just have your cache as a library. From the downsides, you don't have a possibility of flexible management of your caching cluster. If you would like to, you realize, okay, I thought, you know, this distributed cache is enough. We have 3 nodes, but now suddenly I would like to 10 nodes. You can only scale it up together with your application. Also, your cache needs to be written in the same language as your application. And data is collocated with your application, which may be a problem, may not be a problem, depending on your policies in your enterprise. Okay, we covered embedded cache. Next one is client server. So client server is this good old database style. So we will set up the cache server separately and then use cache client to connect to the cache server. This is how it looks like. So again, request goes to our system, it goes to Kubernetes service, it's load balanced to one of the application, and now application uses cache client to connect to the cache server, which is deployed separately. In Kubernetes, it's usually deployed as a stateful set, because after all, cache cluster is a stateful thing. Now, if we compare this diagram, and if we compare this solution to embedded cache, there are two main differences. So first difference is we have a new thing in our architectural diagram. And this new thing needs separate management. So it usually will be a separate team or some DevOps effort to manage the cache cluster itself. But there's also a second difference. So if we compare it to embedded mode, there is also a second difference. And the second difference is this part. This part is the cache client. So think about it. Now the application uses cache client to connect to the cache server, and they use a well-defined protocol in between. So now your application can be written in a different programming language than your cache server. So you are not longer bound to the same language used for the cache, for the implementation of the cache itself. And that is a very common strategy, that you actually deploy cache cluster or multiple cache clusters and connect from multiple microservices written in different programming languages to that cluster. It's so common that in like Redis or Memcache, that is actually the only topology that you can use this client-server mode. How to set it up? So for the Hazelcast, how to start it on Kubernetes? You can use Helm chart, or you can use. We also provide an operator, and with this one command, you already have a cache server deployed. What about the client? So this would be your. If we stick to this example with Spring, this is your client configuration. So you only need to specify, okay, I would like to use Kubernetes. Enable this using Kubernetes plugin, and the client will discover the caching server automatically. So we ended up with the diagram like this. So I can already tell you that in big organizations, managing this cache server is usually done by a separate team, because they manage databases. They also manage cache servers. So if we move to this client server model, we can even go one step further and move this management of this cache server to the cloud. So cloud is kind of a client server, but it's very specific, because the server part is not managed inside your organization. How it looks like. So we, again, like request goes to our system, is load balanced to the one of the application. Application uses cache client to connect to the cache server, but the cache server is located in the cloud. So in the cloud, it means we don't have to worry about all this management part. We basically pay for the cloud provider to give us the cache cluster. How it looks like in the code, in the configuration. So you use CLI or web console to create a cluster in the web, then get like a discovery token, put the discovery token in your client configuration, and that's all. So client will find its way to the cache cluster located in the cloud. Short summary: pros and cons of client server and cloud caching. From the good sides, data is separated from your application, and you can manage your cache cluster separately. So you can scale it up, down, backups, everything you want separately. It's programming language agnostic, because we use cache client to connect to the cache server. From the downsides, you need to have spend some time on managing the server itself, or pay for the cloud solution. And I mentioned here higher latency. So it's not necessarily higher latency, but you have to think about latency. So if you deploy your cache server on your own, like on-premises solution, make sure that your cache server is deployed in the same local network. Because using caching is like, caching is a domain of very low latency. You don't use cache to be slow. You use cache so that your latency is very low and you access your data very quickly. That's the whole point. If you use a cloud solution, you also have to think about latency. So what we do in Hazelcast Cloud, we don't provide the infrastructure. So if you create a cluster in Hazelcast Cloud, you choose the underlying cloud provider, AWS, GCP, or Azure. And you should choose the same cloud provider where your application is running. Next, you should choose the same region where your application is running, because you don't want to access your cache, from one continent to another, because then latency will be huge. But there is one more step. So what we provide is VPC peering. So we create a cluster for you, and you can peer it with your network where you are running your application. So in result, you have, it's like a one virtual local network. That's all because of the latency. So be careful, like with the cloud solution, because you want low latency when you use caching. The next pattern is sidecar. So sidecar is interesting because so far embedded client server, it's not really only for Kubernetes. Sidecar is also not only for Kubernetes, but it's basically only for containerized environments. But it's very, very widely used in Kubernetes. How it looks like. So again, request goes to our system. It's load balanced to the one of the application. But this time in our Kubernetes pod, we have not only the application, but also the cache container, the cache server. And then application uses localhost, connects to the cache server using localhost, because it knows that your sidecar container is always available at localhost. And obviously all these sidecar cache containers, they all form one consistent caching cluster. So this solution is somehow similar to embedded, somehow similar to client server. It's similar to embedded because after all, we deploy cache together with the application. So we scale them up and down together. There's no discovery needed. But it's also similar to client server because you can use different programming language for your application and for your cache server. Because after all, you are using cache client to connect to the cache server. And there is some isolation of data between your application and the cache server. It's on the container level, but may be good enough for you or may not be good enough for you. How it looks like in the code. So in the code, you have, for your client, you have a static configuration to the localhost. But the whole thing is not static, it's dynamic. We just know that cache server is available at localhost because we know that we deploy them together, like here. So we deploy our application together with the cache server in one pod. Short summary about sidecar caching. So from the good sides, configuration is very simple. It's programming language agnostic, low latency, some isolation of data and applications. From the downsides, we don't have a flexible management, and after all, the data is collocated in one application pod. So it's the data and application, they are separated but isolated on the container level, but nothing more. The last caching topology for today is reverse proxy caching. So reverse proxy will be something completely different. It will be completely different because so far the application was always aware that such a thing as a cache exists. So it explicitly connected to the cache. Now we'll do it differently. We'll put cache in front of the application, so the application will not be even aware that such a thing as a cache exists. So this is how it looks like for Kubernetes. So request goes to our system, and now you can have actually cache before your Kubernetes service, after, or like you can even put it in your ingress controller, since ingress is implemented using Nginx. A very I think the best solution for reverse proxy caching is Nginx, because Nginx is everywhere. It's very mature solution, and it's very easy to configure actually. And now the request goes to our system, and if the value is found in the cache, it does not even touch the application. So the application is not even aware that there is such a thing as a cache. If you would like to configure Nginx, that is all you need to add. So you specify, okay, do caching for me, that's it. As I mentioned, Nginx is very good because it's mature, but it also has some issues or some characteristics that you need to consider. So it's only for HTTP, it's not distributed, and it's not highly available. Data is not actually stored on the disk, but it can be offloaded to the disk. So you have to think, because if your data is offloaded to the disk, it means your latency will be different. It's not the case, for example, in Hazelcast, you are guaranteed that your data is stored in memory, so you can make some assumptions about the latency. But still, Nginx, it's a very, very good solution. Now, the last variant of this reverse proxy pattern will be reverse proxy sidecar. So this will be a somehow combination of reverse proxy pattern and the sidecar pattern. So we will just put reverse proxy caching as a sidecar. How it looks like. Request goes to our system, is load balanced to one of the Kubernetes pod. And now inside the Kubernetes pod, it's not the application that receives the request, but it is the sidecar container, which contains the cache server, and it intercepts the traffic. So if the value is found in the cache, in this reverse proxy cache container, it's not forwarded to the application. Only if the value is not found there, we forward it to the application container, and application that performs its business logic. So it's like all this reverse proxy thing, all this fact that application is not aware of the caching, it has some good and bad sides. So it's good, but it's also not good. So maybe let's start from the reasoning why it's a very good idea. You remember this diagram from the beginning of the presentation. So we have a lot of services in different versions, they use each other. This is, by the way, a very small diagram. In reality, we have really a lot of microservices. Now, with reverse proxy pattern, you can look at the system from the, measure the performance of the services and see their interactions, and you can, in a declarative manner, on the configuration level, decide, okay, I would like to add caching here and there, and that's it. You don't touch the code of any of the service. So that is the whole beauty of the reverse proxy caching, that you can, in a declarative manner, introduce caching layer to your system. So how it would look like in Kubernetes? So in Kubernetes, you would have like you're starting from the bottom, you have your application container, then you need this caching proxy container, which contains the cache server and intercepts the traffic. And we also need some init networking to change the IP route table so that the traffic is not received by the application, but by this caching proxy. So if you look at this diagram, it may make you think like of something we actually seen in the previous presentation. So all the service meshes, Istio, because that's the same idea that you introduce some feature in a declarative manner, and not changing the service, the core of the service, but on the configuration layer, you introduce some features. And actually, this there was a support for HTTP caching. There was for a long time there was an open issue, but now it's closed on the Envoy proxy, which means that currently you can use in the Envoy proxy HTTP caching, which means that all the service meshes that are based on Envoy proxy, they will be able to support it. Now, I also mentioned that it's not all good. So this reverse proxy idea. So if we put cache in front of the application, if the application becomes unaware that such a thing as a cache exists, there is one thing that becomes way more difficult. And that thing is a cache invalidation. Actually, if you look anywhere on the internet, like what is the biggest problem with caching in general, that is the cache invalidation, meaning when to decide that your value in the cache is already outdated, it's stale. I should not use it. I should go to the source of truth. Now, if the application is aware of the caching, we can have some business logic to say, okay, if something happens, then don't use the evict the value or just don't use the cached value. However, if the cache is in front of your application, then the only thing you can do is do some HTTP things like basically what HTTP offers, like timeouts, e-tags, basically timeouts. So that is like a biggest problem with reverse proxy caching, or biggest thing that you need to consider when you would like to use the solution. Will I need to have some business logic which decides on the caching? That's the thing. Short summary about reverse proxy and reverse proxy sidecar caching. From the good sides, and the reason why we will use it is it's configuration based. So you don't need to change your application in order to introduce the caching. It's programming language agnostic, it's everything agnostic, because it does not even touch the core of your application. And this is very consistent with the containers and microservice world, Kubernetes. I really believe it will be the future, and like especially with this implementation in Envoy proxy, that it will become a way to go with the caching. From the downsides, we mentioned cache invalidation. There are no major solutions yet, except of this Envoy proxy is not. I don't think it's mature yet, and it's a protocol based. So this was the last caching pattern, caching topology that you can use in your system. And as a short summary, what I proposed as a short summary is not to repeat anything I said before, but as a short summary, I proposed a very simple decision tree, which is probably oversimplified, but at least gives the idea where to look for if you are to decide about your caching solution for your system. So the first question I would ask is, do I need to be aware? Does my application need to be aware about the caching? If no, am I early adopter? If yes, use reverse proxy sidecar caching. If no, use reverse proxy with Nginx. Now, if your application needs to be aware of the caching, then the next question is, do I have a lot of data, security restrictions? Is this caching like really big thing in my for me? If no, do I need to be language agnostic? If no, use embedded cache. If yes, use sidecar. Now, if you work in a big organization, you have a lot of data or some security restrictions, then the last question you need to ask is my deployment cloud? If no, use on-premises client server. If yes, use cloud solution. So this is like a as I said, it's maybe a little oversimplified, but at least gives the direction where to look for the right cache for your system. As the last slide for this talk, I would like to give some resources. So this first one is the source code for each of these patterns. So if you'd like to use them like in practice, how they look, how their implementation looks like, so you can try them on your own. Second link is a blog post about how to set up Hazelcast as a sidecar caching. Third one is a prototype we did for a reverse proxy sidecar caching, but it's on the prototype level, so nothing that you can really use in the production. And the last one is a very good video talk about Nginx as a reverse proxy caching solution. And with this last slide, I would like to thank you, and I'm open if there are any questions.
Thank you very much, Rafał. And Edith, if anyone have a question, feel free to unmute yourself and ask the question, or write it on the chat and I'll read
it. I have a question. In an environment, I'm not familiar with caching, and so my question is a basic question. In a Kubernetes environment, when we have a Redis in place, we can leverage Redis as a sidecar proxy in each containers, or we can have a Redis as a cache server, and the containers can talk to the Redis server. Which one is the best one?
I would say all these pros and cons applies to Redis as well, because it's like I made examples with Hazelcast, but actually because I work for Hazelcast, that's it. So I know Hazelcast better, but it all applies to Redis as well, because Redis is also a distributed caching solution. So I would say like to use sidecar or to use client server, it will depend on your needs. What I see people are doing, if they very frequently use Redis as a sidecar for a simple, not even non-distributed caching with microservice and client server, then they really set up like the whole Redis cluster with replication, etc. But as I said, like all this and what I said like applies to the Redis as well.
So we can have both Hazelcast or Redis. We can have some sort of the Redis distributed cluster in the Kubernetes. So the all caching system talk to each other, and we have the updated caching system for all of the containers. Correct me if I'm wrong.
Yeah, sure. It's the same with Hazelcast and with Redis. Both are distributed caching solution. Distributed means that you form a cluster and then you have all applications, they use the same data basically.
Thank you.
The question from my side, to follow up on that, what do you do if you have production and non-production workloads on the same cluster? Then I guess you just spin up two caching clusters to separate them, or can you somehow separate production from staging on whatever within one cluster, one caching cluster, I mean?
Yeah, if you normally I would say like if you have like staging environment production, you should even have like separate Kubernetes clusters. But if
of course, but some people still run it in the same.
Yeah, but if you run it the same, then it's the same like with the databases. So like it's actually better to have separate caching clusters. But if you really don't want to do it for some reason, like cost, for example, the cost can be the reason, then you can separate them. You know, you just use different cache names for the staging and for the production. So like to give your analogy to the database, you can use the same database, but with different schemas. With different So it's the same applies here. But normally I would prefer to have the best solution is to have separate Kubernetes clusters. Second best is to have separate caching clusters, and only if you for some reason don't do it, then just use different cache names so they don't collide.
Yeah, okay. Do you handle somehow in Hazelcast the situation that so I had a problem with one of the caching solutions I built for the client as well, that when, let me think, what was the problem? The problem was that when clients send the request, then it has a lot of parameters in URL, and then server replies, and then the client contacts server again, but it usually all these parameters are mixed. They come in random order. So then the cache, even though we requested this exactly the same resource, just because the parameters in the URL changed, the cache thought that it's a different resource, so then it wasn't cached. So then, like, if we have 20 parameters in the URL, then we end up with 20 entries in the cache for exactly the same resource.
Mm-hmm.
So the solution for us, because we built it based on Nginx and Vagrant. So the solution for us to use like a plugin for Nginx, which will sort the parameters always in the same order. I'm just wondering if you have something for that in Hazelcast.
No, simple answer is no. I mean, if you use like this reverse proxy in general, then yeah, that's the only thing you can do is this. What you did actually, have like an extension or plugin to Nginx. But if you cache at the application, if the application is aware of the caching, then you can always sort it out at the application level. So not cache the request directly, but application can sort these parameters. That's
yeah.
But as a Hazelcast, no, we don't provide such like a solution to this problem. Yeah.
Mm-hmm. Okay. Anyone? Any more questions? Actually, I have one more. You didn't mention this on the presentation, maybe because it's obvious, or maybe I'm missing something. But when you use cache in Sidecar, then also the huge cons is that every time just pod dies and being restarted, and the cache also being wiped out, right?
No, because like if you use distributed cache, if you use just a cache, then yes. But if you use distributed cache, then if one pod dies, you don't lose the data actually, because like yeah.
I mean when we have cache in the sidecar of the application, as a sidecar of the application.
Yeah, but if you use just simple caching, then yes. But if you use like a distributed caching, let me just go back to this. Where was it? Here. Yeah, sidecar. So you see like all these cache containers, they form one caching cluster. So if one of them dies, you store actually the backup in some other container. So if one of your pod dies, you still don't lose this data.
Yeah, okay, but that's different. I was talking about the situation. I think you had it also on one of the previous slides, when you basically just have simple cache in each application container.
Yeah, sure. Yeah. Then yes, sure. Yeah. Then it's like an embedded in a sense that if your application dies, then your cache data dies. Yeah. Actually, you're right.
I have a question regarding the sidecar cache. Is there any so Hazelcast is an open source solution, or it's a proprietary software solution?
Yeah, it's open source. You can use it. Yeah. We have an enterprise version, but it's nothing I mentioned here is actually an enterprise feature. So it's like everything I mentioned here is open source.
Okay. And is there any you shared some links, and is there any Vagrant file or somewhere that we can do a quick POC for or based on Hazelcast?
In Kubernetes, it's like what we do is if you'd like to play with this, let me maybe show you. Like we have a site called Guides Hazelcast, and if you're interested, it's like we have a lot of like you just follow very simple guides how to set it up on Kubernetes, connect your application, embedded mode. For example, like if you look at the first, it will walk you through your how to set it up. It's actually pretty straightforward. So
Okay. Yeah, got it.
Yeah.
Okay.
So it's like to create just caching cluster, you just need helm command, plus adding the repository. But this one command will create a cache cluster for you. So it's actually very super simple.
Okay, got it. Thank you.
Okay, anyone, any more questions? If not now, then I guess you can find Rafa Weasley on Twitter and ask him any questions later on. So
Sure.
I think
I'll be happy to answer any questions. So just ask it on Twitter. So really, if anything is on your mind, I would be happy to answer.
Yeah, so I think I would like to thank you again, Rafa, for the talk, and I would like to thank you again, Jörg and Hanna, for the previous talk. And we can spend a few more minutes if anyone wants to talk about anything cloud native related. Otherwise, we'll be closing shortly.
I can just ask a question, general question, and if anybody have some thoughts about that, please share. It's not related to this meeting, but this is a cloud native. So one question is that what operating system or which operating system is good to use in the Kubernetes environment? It's a containerized operating system, for example, Linux Flatcar or Fedora CoreOS or something like that. Or we can use the general operating system such as Ubuntu Minimal or something like that. If we can discuss it, it would be great. Just one idea to share thoughts.
Sure. Yeah. If anyone wants to answer, feel free. From my side, to be honest, for a really long time, I also didn't care about that because, when you are in the cloud, then you usually don't care about it at all, because most of the companies I work with these days, they just use managed Kubernetes clusters. So you don't touch the nodes at all. When you actually want to build your own Kubernetes cluster, so you actually need to provision machines. Then most what I've seen, people were using CentOS just because it became kind of the standard. Although, they recently announced that it may change. So so that may change. And when we are talking about really advanced stuff, like really custom built clusters, then it was CoreOS for a long time, but then it died as well. So I think most folks will move to Flatcar nowadays. But I didn't touch like really raw infrastructure for a long time. Most of the companies are moving to managed Kubernetes these days. Okay. All right. I think then we'll be closing. No more questions I see. Then yeah, thank you again, everyone. Thank you for the talks. Thank you for to our guests, and yeah, hopefully see you on the next software Circus. Thank you very much. Bye bye.